So in this final topic, we're going to discuss about few major drivers behind the advancement of nanomaterial. When we read about the advancement of nanomaterial, we always come across the name Richard Feynman and his lecture. There are many articles in the scientific journals that talk about his vision and contribution towards nanotechnology. Richard Feynman arguably laid the conceptual foundation for the nanotechnology. In the annual meeting of the American Physical Society at California Institute of Technology, Caltech, on 26th of December 1959, he delivered a famous lecture with the title, "There's Plenty of Room at the Bottom." It is important enough that 25 years later, Richard was invited to give an updated version of "There's Plenty of Room at the Bottom" at a week-long seminar at the Esalen Institute in October 1984. The importance of his lecture can be seen by the proceedings event that took place, such as the invention of the scanning tunneling microscope. In his lecture, he highlighted about the following. The first is about writing 24 volumes of the Encyclopedia Britannica on the head of a pin, hinting miniaturization of data storage and basically computer. During his lecture, he even offered $1,000 to the first person who could reduce the page of a book to be readable by an electron microscope. And it is not long after that the challenge has been completed by few students that use the scanning tunneling microscope to manipulate individually atoms to create small and smaller letters. He also suggested that it would be possible to arrange the atom the way we want, inspired by the cells as the building block in the human body. He said a physicist should be able to synthesize any chemical substance by putting the atoms where the chemist says. He also called the researchers or the scientists to improve the resolution of the electron microscope. He also talked about how nano-objects can solve issues regarding lubrication in engine, which is a big issue during that time. And he also mentioned about nanomachines, which he called tiny hand, that helps us to interact with the nano-scale object. Most of his predictions not only came true, but in some cases exceeded expectation. After all, after 6 decades of innovation and research, there is still room at the bottom. This diagram represents the nanotechnology race set in motion by Feynman lecture between various disciplines from 1940 until now to get smaller and smaller. It also shows the evolution of the fields related to nanotechnology. In 1940, in electrical engineering, the size of each electrical component are large, that eventually make the size of a computer into several meters. In biology, the focus is at the cellular level in the micrometer scale, while chemistry has already started to focus about the smaller scale. In 1960, the electronics components are already in the size of few millimeters, while biologists are now focusing on the molecular biology. In 1980, electronics has now evolved into microelectronics in pursuit of ever smaller device into the limelight. The evolution of this miniaturization has been brought about by the tremendous advances in the semiconductor industry and the ability to produce smaller and smaller integrated circuits. However, starting from the year 2000, most of the field has overlapped with one another and a lot of new application has been developed. For example, nanomedicine evolved from the classical life science disciplines like molecular biology and biochemistry. From microelectronics become nanoelectronics, biology and engineering combined to become bio-nanotechnology. So we'll talk about 4 major drivers behind the advancement of nanomaterial, which is electronics, which is the field of molecular biology, material sciences, and engineering, and also quantum nanoscience. In electronics, the continuous scaling of device size in the complementary metal oxide semiconductor transistor has been the fundamental driving force in nanotechnology in last several decades. And this trend can be represented by Moore's law. According to Moore's law, developed by Gordon Moore, that the number of transistors in a chip will be doubled in every 2 years. So therefore, in a graph of the number of transistors in a single chip versus year, it should show a linear trend. Taking challenges from Moore's law, scientists and engineers have been able to relentlessly push down the limits. And today we are able to pack more than 1.9 billion transistors into one chip compared to 60 transistors in the same area 40 years ago. However, even Gordon Moore himself acknowledged that his law cannot be sustained forever. He noted in 2005 that eventually transistor size will reach the limit of atomic size, which is the fundamental barrier to scaling. So the continuous miniaturization efforts has actually drives towards the development of new kind of nanostructure that can have more and more transistors inside a single chip. The second field that drives nanotechnology is molecular biology. Since living organisms which are made of one or more cells are in the size of roughly 10 micron, each individual cell will be smaller in the submicron size. But if you compare the size of a cell with a nanoparticle, it is actually 1,000 times bigger. But protein are typically 5 nanometer in size, which is comparable to the size of nanomaterial. This simple size comparison gives an idea of using nanoparticle as a very small probes that would allow us to spy at the cellular machinery without introducing too much interference and without destroying the cell. So therefore, we can send a specially designed nanoparticle to kill an individual cancer cell without killing other healthy cells, for example. We can also use a special nanoparticle as a marker for imaging and sensing application. Understanding of biological processes on the nanoscale level and the urgency to find a much safer and effective cure for various diseases are one of the strongest driving force behind the development of new nanomaterial. Next, we're going to talk about the material science or material engineering. Material science or material engineering is an interdisciplinary field applying the synthesis, characterization, and properties of material to various areas of science and engineering. So we have physics inside, we have chemistry, we have part of mathematics, and we also have engineering. What properties we are searching in a material? So the answer is strength. We're looking for strength, hardness, flexibility, thermal, magnetic, optical, and electrical properties, stability, catalyst, reusability, eco-friendly, and biocompatibility, and also low cost. To be able to find a material that suits our need, we need to get into a nanomaterial, since nanomaterial will provide a lot more room for tunability. The nanometer length scale is the largest one over which a crystal can be made essentially perfect. The ability to precisely control the arrangement of impurities and defects with respect to each other, and the ability to integrate perfect inorganic and organic nanostructure holds forth to the promise of a completely new generation of advanced composite. Another drivers of nanotechnology is the quantum nanoscience or nanotechnology. Based on the timeline, the quantum mechanics have been developed long before the birth of nanotechnology. So the race into probing into the quantum world is what accelerates the progress in the nanotechnology field, since the majority of weird phenomena in nanomaterials can only be explained using quantum mechanics. Quantum nanoscience is a new basic research area at the intersection of nanoscale science and quantum science that creates the understanding that enables development of various nanotechnologies. It uses quantum mechanics to explore and utilize coherent quantum effects in engineered nanostructure. And this may eventually lead to the design of new types of nano device and nanoscopic scale material. So in summary, in nanotechnology we have various disciplines we require a true interdisciplinary efforts in various disciplines. So that's all. If you have any question, you can post in the comment section or just email them to my email at munzir@usm.my. Thank you for your attention and all the best.